Good morning, everyone. Today we're going to continue our look at sequences, and today is actually going to be a little bit more mathy, I guess is the correct word, more mathy than the previous day. So let's get started at the next window. And we have now in Cairo, Indiana Jones and his colleague, Salah Mohammed Faisal El-Kahir. I hope I got that right. They set about relaxing for a moment eating dates, and they are joined by the French mathematician Augustin Louis Cauchy. If the dates on the plate are numbered, can you tell which is the last date each person will eat? Okay, the date eating sequence in the Raiders of the Lost Ark is a pretty big one in my head for some reason. Don't know why. So what do we have? We've got 3, 8, 13, 18. Salah is 1/2, 2/3, 3/4, and 4/5. And Cauchy is 1, 3/2, 5/3, and 7/4. So we're going to find explicit rules for Indiana, Salah, and Cauchy. Indiana, that is just a arithmetic sequence with the first term of 3 and a common difference of 5. So from what we learned yesterday, it's 3 plus n minus 1 multiplied by 5. I'm not going to worry about simplifying that. Salah, we've got 1/2, 2/3, and 3/4, and 4/5. And it doesn't look like the numerator and denominator are related to each other at all. So when that happens, I often take a look at the sequence of the numerator and then the sequence of the denominator. So if this is the first term, if S1 equals 1/2, then I take a look at the 1 and the 2 separately. S2 is equal to 2/3. Okay, so we're going to relate both the numerator and the denominator with the index number. And let's take a look at S3. S3 is equal to 3/4. And again, let's try to relate the numerator with the index number. And it looks as though the numerator is always the same as the index number. So we can say Sn is equal to n on the numerator. Now we look at the denominators, and we see that the denominator is always the index number plus 1. So 3 plus 1 is 4, 2 plus 1 is 3, 1 plus 1 is 2. So we make our denominator n plus 1, one more than whatever number is in the index. So that is that's neither arithmetic nor geometric. Let's do the same thing with the Cauchy formula. C1, we have 1/1. C2, we have 3/2. C3, we have 5/3. And C4, we have 7/4. So immediately, the first thing that jumps out is that the denominators are the same as the index numbers. So if that's true, that means we could just put an n in the denominator. Looking at the numerator is an arithmetic sequence, 1, 3, 5, 7, where the first term is 1 and the common difference is 2. So we can put the arithmetic sequence formula in the numerator now. That gives me 1 plus n minus 1 times 2, or 2n minus 1. So those are the three explicit rules for Indiana, Salah, and Cauchy. Looking at the numerator and denominator separately from a sequence that has rational terms, that's often going to be the key to figuring out the explicit formula. Now, I don't think that you probably would have imagined that limits would be coming back into existence, but they are. If we take a look at Indiana's sequence, it just keeps growing and growing, and it doesn't stop because it keeps increasing by 5 units every time. So what we would say about Indiana's limit, the limit as n approaches infinity of in is the same as the limit as n approaches infinity of 3 plus n minus 1 times 5, and that's equal to infinity. Let's do the Sala limit. Okay, so the limit as n approaches infinity of Sala's sequence is the limit as n approaches infinity of n over n minus 1. Now, especially for these sequences that involve ratios, one of the most common things that we are going to do is divide everything by the reciprocal of the highest power. So in this case, the highest power is n to the first power. The reciprocal of that is 1 over n. So we're going to multiply both the numerator and denominator by that reciprocal. Okay, and that's going to give us a bunch of fractions, really. Let's see, let's simplify that out. We get 1 over 1 plus 1 over n. And although you would never write it, you would think this is true. And it is true, property-wise. The limit of the quotient is the limit of the numerator divided by the limit of the denominator. But wait, look at the denominator. The denominator is a sum. So this is the same as the limit of 1 over the limit of 1 plus the limit of 1 over n. And that is really nice because the limit of 1 is just 1. The limit of 1, again, is just 1. And then the limit of 1 over n, that's always equal to 0. So it seems as though this limit is equal to 1. I would probably, again, never write all of those intermediary steps. That's more of a mental exercise, and as you do limits, you'll get pretty good at that. And that's the limit for Sala. Let's look at the limit for Cauchy. We have the limit as n approaches infinity of the Cauchy sequence. That's going to be equal to the limit as n approaches infinity of 2n minus 1 over n. And again, we look at the highest power here is n to the first. So I'm going to multiply that numerator and denominator by 1 over n. Simplify that. And then you can just take all of these sequences. You've got constant minus this limit over here is 0. This over here goes to 0. So it's just 2 minus 0 over 1. So this limit is just equal to 2. So that was a really quick jump start into how we're going to compute limits. And whatever day it is, you're going to mark on your calendar that this is the first day that we heard the word converge, convergent, and divergent. These words are going to be kind of the obsession of the next chapter especially. So, yeah, kind of get used to that. So a convergent sequence is a sequence that has a limit. As n approaches infinity or whatever number, the sequence, the terms, approach a limit. And we just figured out all those limits, so we know which sequences are convergent, and we know which sequence was divergent. So just comparing what we see here, we can see what the difference here between convergent and divergent. And if you don't see it, yeah, look here. Now, this is kind of cutesy, but rather than a theorem about Sala eating sandwiches, the sandwich theorem allows us to mathematicians to calculate more difficult sequences indirectly. And that's the key, indirectly evaluating sequences, by sandwiching the difficult sequence with two easier sequences. So take, for example, the sequence cosine of n over n. So we know for sure that cosine is between -1 and 1. And if that's true, just with dividing everything by n, we get -1 over n is between cosine n over n. Sorry, cosine n over n is between -1 over n and 1 over n. Over here, next, we also know the limit as n approaches infinity of -1 over n, that's equal to 0. And then the limit of 1 over n as n approaches infinity, that's also equal to 0. Now that you know that, you're ready to actually complete the proof here. So the first inequality that we had becomes a limit inequality, 1 over n and the limit of 1 over n over here. And these two limits, this limit right here is 0, and this limit right here is also 0. And that tells us that the limit of n approaches infinity of cosine n over n is greater than equal to 0 and less than equal to 0. So it's got to be between 0 and 0. And there's only one thing between 0 and 0, so it has to be also equal to 0. That's how the sandwich theorem works. We show the limit on the left is equal to the limit on the right, so the limit in the middle has to be the same as the limit on the left and the limit on the right. We're going to transition here to something called an alternating sequence, and alternating sequences seem innocent enough, and maybe they don't seem innocent, I don't know, but maybe they sound kind of complicated. But alternating sequences are really going to be kind of a savior. We know a lot of things has to happen for an alternating sequence, and there is a special theorem called the absolute value theorem. And the absolute value theorem states that if the limit of the absolute value of a sequence is equal to 0, then the limit of the sequence without absolute values is also equal to 0. This is restated as if the absolute value of a sequence converges to 0, then the sequence will also converge to 0. Seems like it's not a big deal, but it really will help us out, especially if we can identify those absolute values sequences. So let's start by proving this is true. We've got, given that the absolute value of a sequence is equal to the limit of the absolute value of a sequence is equal to 0. So we're going to go with the terms, both negative and positive. So this says that the negative absolute value is less than or equal to the term number, and it's also less than or equal to the absolute value, the positive absolute value. Why is this true? Well, we've got the negative of the absolute value is always negative, and the absolute value is always positive. So basically, any term has to be between a positive and negative number and itself. So it's got to be somewhere in its own region, I guess is the way that we would say that. By way of example, let's take the absolute, or let's take -6. -6 is definitely greater than equal to negative of -6, greater than or equal to that, because this is absolute value of -6 is 6, and the opposite of 6 is -6. So that's true on the left side. And on the right side, we have the absolute value of -6, which is +6. So this says that -6 has to be between -6 and +6, which is true. And that's going to be true no matter what number you put in there. Well, that was a very long explanation. Let's move on to the second box. The limit as n approaches infinity of the negative absolute value is equal to 0. And the explanation here is kind of a long one, but if we take the limit of the negative of the absolute value of a n, Well, the negative and the absolute values don't really play a part in the limit. So we can just kind of take the limit and move it to where it's needed, which is at an. So negative absolute is equal to the negative absolute value of the limit of a. And we know the limit of a is 0. And then the negative absolute value of 0, well, that's just 0 as well. So we're going to substitute now, and we know this left side is 0. And we are given that this on the right side is 0 as well. So we're going to put those limits here, and then we're going to apply what those limits are. The limit of the left side is less than equal to the limit of the middle, is less than equal to the limit of the right side. And then by sandwich theorem, we show that the limit of an is also equal to 0. So there's our sandwich theorem. Going to prove this alternating absolute value theorem for alternating sequences. And that kind of brings us to our important ideas. Actually, before we get there, let's apply that absolute value theorem. Let's take a look at the limit as n approaches infinity of -1 to the n over 2n over 5 plus n. Okay, if I was going to write out the terms of this sequence, I would see that the terms of the sequence are 2 over 6, -4 over 7, 6 over 8, -12 over 9. Notice that the terms of the sequence change from positive to negative to positive to negative. This is an alternating sequence. And what makes it alternating is this part right here, the -1 to the n power. That changes the term from negative to positive to negative. You can see the action that the exponent of -1 plays in that. So if this is an alternating sequence, what I really need to do is look at the absolute value of this. And that's just equal to 2n over 5 plus n. Now, if I know that that's true, I can check this limit, and we will check this limit. But if this limit is equal to 0, then the limit of the non-alternating sequence, the original sequence, is also going to be 0. And if it's not equal to 0, then actually the limit doesn't exist. So let's take a look at the limit of 2n over 5 plus n. We've already learned that we need to divide each part of this by the highest power of n. And then after we divide by the everything by n, we're going to simplify. And now the only thing that has an n would be this term right here, and that's going to go to 0. So this limit is just going to be 2 over 1, or just 2, which is not equal to 0. Therefore, the limit of the alternating sequence, -1 to the n, multiplied by 2n over 5 plus n, does not exist. And that's how you use the absolute value theorem. If this limit over here turned out to be 0, then we would have said that the limit was also equal to 0. So for an alternating sequence, either the limit is 0 or it doesn't exist. So either the limit of an alternating sequence as n approaches infinity is either 0 or it does not exist. Those are the only two options. Okay, so now we're ready for our important ideas. We've got the limit properties that we were using earlier. There's usually no reason to think about these limit properties because we kind of know them almost intuitively. So the sum and difference or product works like you think it should. Constant multiples work like you think it should. Quotients work like you think they should. We have the squeeze theorem, or the sandwich theorem, I guess is what they call it. Sandwich theorem, depending on which book you're using. which we discussed also, and I'm saying that is great for sine, cosine, etc. And then maybe the most important thing here is the common trick. Divide each term by the highest power. So let's check our understanding. We're going to go with number 1, this limit of n over 2n plus 5. It looks like the highest power here is n to the first power. So let's divide everything by n. We get the limit of 1 over 2 plus 5 over n, which is equal to 1/2, since 5 over n is going to go to 0. All right, that's great. Let's check this one. The limit of, as n approaches infinity, of negative 1 to the n, 5 over 3n minus 1. Like last one we did, we're going to go ahead and apply the absolute value theorem. So the absolute value of the general term here, negative 1 to the n, 5 over 3n minus 1, that's equal to 5 over 3n minus 1. Same trick, divide everything by the highest power of n. We have a couple of different parts here that will trend to 0. And if I evaluate that, I get 0 over 3, which of course equals 0. So since the absolute value of our limit goes to 0, then our limit will also go to 0. That's the other part of the absolute value theorem that we were talking about earlier. Finally, we're going to use the sandwich theorem to evaluate 1 over 3 to the n power, the limit, and our hint is that 1 over 3 to the n is always less than 1 over n. And that's true because 3 to the n is always bigger than n, as n goes to infinity, of course. So let's sandwich this. Now we know, of course, that the right side of this is going to be 1 over n. But what do we put on the left side? And the trick here is to put the opposite. We're going to put the limit as n approaches infinity of negative 1 over n. Now we know both of those limits because these are very well studied. So this, on the left we get 0, on the right we get 0. And look at that, if the limit on the left side is the same as the limit on the right side, then by the sandwich theorem, we know that the limit on the middle also has to be the same. So that's it for us today. Hopefully this wasn't too difficult. That thing about dividing by the highest power of n, that's actually really key to evaluating most limits. So with that said, I will see you guys later, and have a good one.